This is video 6 for week 7, and we are on page 180 in the textbook, but that's not important to know. The question is to sketch 3x to the 5th minus 5x cubed. Now, we can use those quick methods that I showed you. It's actually really, really easy. I can just factor out x cubed, and I get 3x squared minus 5. And that's telling you we have a triple root here at 0. And then we have this other thing over here, which is two roots kind of stuck together. And we just use the quadratic formula to find that. Or you don't have to use the quadratic formula. It's actually really easy. But if you want to, you can go ahead and use the quadratic formula, but I'm not going to. 3x squared is 5. X squared is 5 over 2. So x is either, over 3. So x is either plus or minus square root of 5 over 3, which is approximately 1.3 for purposes of plotting. So I want you to consider what this guy looks like all by itself, this piece, this 3x squared minus 5. If we were just going to plot it all by itself, it would look kind of like this. It would have a min down here at the origin, below the origin at 0, negative 5. Okay, and then these roots that we just found, plus and minus 1.3, they'd be right about there. Okay, so what would this guy over here look like? This x cubed just looks like we know it looks like. So what are you really doing? You don't need calculus to do this problem, but you have to kind of like figure out what's going on. If you multiply this plot with this plot, what happens? So you kind of guess what's going on, sort of piece together, figure it out, what's going on. We have a triple root here, and a single root here, and a single root over here. But you look at this guy, he's going off to infinity at the end, so we're going to eventually go up in quadrant 1, right over there, okay? And we know this is a regular old root. The other thing you notice about this problem is there's this symmetry. You only have an x cubed term and an x to the 5th term, and those are both odd functions. And what that means is any point that's over, let's say, quadrant 1, there's going to be, if you rotate about the origin, take the whole picture and rotate it 180 degrees, there's going to be another point over there. All right, so draw this thing, spin it around, and you get the same thing on the other side. So let's see what's going on. If we have these guys over here, we have to have these guys over here. So you'd be tempted to do this kind of thing, and that's not quite right, but it's the right idea. But we have an x cubed root here. We have a triple root here. And so when we come in, we have to come in flat. So it kind of kinks funny. There you go. That looks really weird, but that's really what it would look like. Okay. So let's see. Let's try to do the same thing using calculus. All right. We're going to try to get the same information using calculus. F equals 3x to the 5th. Minus 5x cubed. Okay, let's take a derivative. We get 15x to the 4th minus 15x squared. Factor out whatever's common. We find out that the derivative is 0 at the origin, not surprising, but we also get another 0 derivative somewhere else. Where do we get it? Plus m minus 1. Aha. So you can see that this question was really rigged to work out nicely. This is why there's this symmetry, this 3x to the 5th, 5x cubed, because we end up multiplying 3 times 5 in both cases, and that allows us to factor out the 15 and get a very nice x squared minus 1 left over. So this is evidence that somebody designed the problem to be nice for you. Now, if this were a cubic, we could use special tricks for cubics, but we don't, so we can't do that. But these are critical points, and now we have to look for suspected points of inflection. Okay. Gotta find second derivative. I'm going to go back up to this line to find the second derivative off of that guy. 15, you double it twice, so you get 60 x cubed minus 30x. Okay, so all we can factor out is a 30 and an x, but that's still useful. So you get 2x squared minus 1, not too shabby. So we get possible point of inflection at x equals 0. And what's the other thing? 2x squared minus 1 is equal to 0. 2x squared is equal to 1. X squared is equal to 1/2. X is equal to plus and minus square root of 1/2. Okay? So that's how we do that. So this guy, these are our other suspected or possible points of inflection. So now we have a collection of, well, a total of 1, 2, 3, 4, 5 possible points that we need to classify. Let's take a peek up above and see if this is consistent with what we already know about the problem. So we know this is about 1.3 over here, but that doesn't even show up in the calculus. Right here, this max and this min, those should show up at 1 and -1. And what else did we say was going on here? 1 over square root of 2. Yeah, plus and minus square root of 2. Where was that? So this is probably going to be here, and then it looks like there's another point of inflection at 0. So we are happy because what we've already figured out without using calculus matches what the calculus is trying to tell us. So we're going to go ahead with the calculus pretending we don't know all that, but we're pretty confident because everything's matching up pretty nicely. Right, so all we need to do now is we need to find the y coordinates of these guys. All right, so f of 0 is 0. That one's easy. F of 1 is 3 minus 5, which is -2. F of -1, so when we put a -1 in here, it's still going to stay -1. So it's going to be -3, and then x cubed is going to be -1. So that's going to turn that into a +5. So we have 3 of our points already figured out. We've got our max, our min, and 1 of our points of inflection. F of 1 over square root of 2. That's going to be, let's see, 3 times 1 over square root of 2 to the 5th minus 5, 1 over square root of 2 to the 3rd. And you know what? You can either use your calculator or don't worry about it. So, calculator. This is just too tedious to do by hand. And then the same thing for the minus 1 over square root of 2. Okay? And let's see what's going on over here. So one thing you might want to do is just justify for yourself that these little green points actually, so for example, this little point at minus 1 over square root of 2, you just want to make sure it's dropped below this max here. So that would be useful information, and we wouldn't have to calculate the whole thing. We just want to make sure, in this case, it's dropped below 2. You see, the max was 2. So we want to make sure that this value here at -1 over square root of 2, we want to make sure that that's below 2 as a way of sanity checking what we did. Okay, so we're going to do something like this. 3 over 1 over minus 1 over square root of 2 fifth minus 5. Write all this stuff in. Is this less than 2? Well, you might want to pull out your calculator because I don't want to calculate 1 over square root of 2. 1 divided by 2 to the power of 0.5 equals 0.707. If you recognize that as 1 over square root of 2, then, well, it is. It's also square root of 2 over 2. And we multiply that by -1 and raise it to the 5th, things like that. You see, it's getting smaller. So even if I multiply that thing by 3, that's pretty small. And it's negative here. This is going to be like -0.53 here. Let's try to do the same thing for the other piece over here. It was a 0.707. So we had a minus 0.707, okay, equals to the power of 3 equals times -5. Okay, then it's going to be plus 1.7. Okay. So 1.7 minus 0.5 is definitely less than 2. It's roughly in the vicinity of like 1.2. So it matches our plot. So we're pretty happy. I'm not going to bother testing the other point, but you can if you want. You kind of just see how you poke around at it. So this guy is at about 1.2 roughly. So I would say that's the y height at that point. Okay. How else would we worry about classifying these guys? Right. So because we already figured out that at this point at y equals minus 0.707, you know this point is lower than we are over here at -1. And then we also know that we have a 0 over here. This is kind of good. This is justifying the fact that this guy is a max. Okay, this is our showing all work, because this problem is a little tricky. You can use these things that we're talking about, the second derivative test or the first derivative test, but it's just it hurts you nothing to just test points on either side. That's totally fair. Okay, and you're going to do the same work. You're going to actually do exactly the same thing to show there's a min on the other side. Okay. Now you may ask, okay, how do I know how to classify that point at the origin? And that's a pretty good question. Okay. In that case, let's just test a point on either side just to see what's going on. Or we could test the derivative on either side. Let's do it both ways. Okay. If I test a point on either side, hold on a second. 3x to the 5th minus 5x cubed. It's still 0. But f, and I just did that for the sake of argument. But what if we go a little bit to the right? You're going to end up with 0.00003 minus 0.005. The only thing I want to know is it positive or negative. Okay, so I have the bigger piece has the minus sign on it. So the only thing I care is that it's negative. What about if I go to the left at this point? Then I'm going to get 3 times 0.1 to the 5th, but there's going to be a negative that comes out. And again, if I put a negative inside the other argument, I'm going to get 0.01 cubed. This minus is turning into a plus. All it's going to do is just flip these signs around. Or again, you can plug it into your calculator. It's fine. But the important thing is, we went from being positive to negative. And then we look at the plot. Did we do that? Yes. We went from being positive on the negative side and then negative on the positive side. So our plot agrees with our calculations. That's how we would test a point on either side of the origin. But what if we would prefer to test the derivative on either side of the origin? I mean, it's not necessary to do both of these. It's definitely not necessary to do all this. I'm just giving you options here. So what if I wanted to take the derivative of these guys instead of actually calculating the points there? So we look up above. We say, well, all we care about is the sign, the SIGN. So since x squared has to be positive, we really only care about the sign of x squared minus 1. So we ask, what's the sign of x squared minus 1? Well, let's see. It's not equals anymore. It shares a sign with x squared minus 1. So actually it's going to be negative. And this guy also shares the sign with x squared minus 1, and it's also going to be negative. Okay? So in that case, using the first derivative test, this point at the origin, we know we're decreasing to get down into it, and then we're decreasing again afterwards, which is consistent with what we said before. We were going from positive down to 0, and then down to negative. So both of these tests are serving the same role. They're doing exactly the same thing, but using a slightly different mechanism to do the same thing. Okay? So there you go. You have some tools at your disposal. You use them as you wish to piece together the pieces of the puzzle and figure out what's going on. And then you plot it. And my favorite tool, like I've told you before, I'll tell you again, my favorite tool are these quick plotting tools. And if you can get the whole picture that way, then all you have to do is take a couple derivatives and poke around a little bit and justify what you're doing, because your intuition is driving the whole process. And then the calculus is kind of there to just back you up on that. Okay? Thank you.